Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're here today to hear a seminar from Curtis Mobley of Sequoia Scientific on recent and future advances in ocean color remote sensing.
Okay, and I assume that he's hearing me okay on the lavalier mic. Okay, so basically for the others of you here, what happened is Dan Fay went off to some National Academy of Science meeting saying he was interested in computationally intensive earth science problems, and they said you should talk to Mobley, and I'm just down the road in Bellevue, so that's how I got here today. So what I'll do is kind of three things. First of all, since I don't know what the audience is here, I'll give you some basic definitions and historical perspectives, and I already know Rob knows that, but it needs to be there for completeness. And then I'll sort of show you some of the work that people like myself have been doing over the last few years to do fancier things with better resolution and more wavelengths, blah, blah, blah. And that will get you up to kind of the state of the art in ocean remote sensing. And then I'll finish up with what you're probably interested in, which is the computational aspects of what's coming in, the next 10 years or so. So let's just get started. What I'm going to be doing is flying over the ocean either in a satellite or an airplane and measuring the light that's coming up from the ocean. So my basic variable here is the radiance. If I have an instrument that's got a collecting tube on it so it only looks at a small range of angles, I put a wavelength filter in it. I can put a polarizing filter on it if I want to. And I'm basically going to measure the radiant power, so let's say watts per square meter, in a small solid angle, so many steradians, and per unit wavelength interval, nanometers. So if I know the radiance, I know everything there is to know about the light field. The problem for remote sensing is if I'm flying over, looking at a spot on the ocean, I'm measuring some radiance, and then the sun goes behind a cloud, well, the sun's input changes by a factor of 10, the output changes by a factor of 10, and the radiance itself is not all that useful for figuring out what's going on in the ocean. So therefore, people usually normalize the radiance by some measure of how much light is coming in, and then that ratio stays fairly steady and can be used to tell me something about what's going on in the ocean. So I'll normally talk about one measure of reflectance called the remote sensing reflectance, which is the standard thing that people in this world use. And my game, of course, is for what gets called ocean color remote sensing, is measuring radiance and then using that to derive ocean environmental properties that could be in-water properties like chlorophyll or sediment concentrations, could be bottom depth, bottom type, or whatever if it's in shallow water. Okay, and then if you're not familiar with the whole game here, basically I'm up here in a satellite looking back down, and I'm just measuring the total radiance that's coming up. Now, part of that is sunlight that was scattered by the atmosphere up into my direction, and so that's called atmospheric path radiance. Part of it is sunlight that's reflected off of the sea surface. That's called glint radiance or surface reflected radiance, and that's noise to me also. And then the part that I'm interested in is the light that got into the oceans, got changed by what was in the oceans, maybe bounced off the bottom. Part of that gets out of the ocean, that's water leaving radiance, and gets up to my sensor, and that's the signal as far as I'm concerned. The problem, of course, is you can only measure the total, and you don't know how much of the total comes from the various pieces. So to just show you an example of the problem, here's numerical simulations for a particular station off of Hawaii, certain, tropical atmosphere, et cetera, et cetera. And so here, the blue line, we're looking at the top of the atmosphere total radiance, and this is bend in 10 nanometer bends. So there's what my satellite measures. But of this, the yellow curve here is the atmospheric path radiance. That's most of the signal over the oceans, typically about 90%. The red curve is the surface glint radiance that's reflected off the surface, made it back up to my sensor. And so I need to take this measurement, figure out this part, figure out that part, subtract those two out, and I'm left with the green curve, which is actually my signal, which tells me what's going on in the ocean. So I'm not going to go into this atmospheric correction business except to bring a little bit back at the end, but just keep in mind that we're starting with big numbers. We finally end up with a small number, and then a guy like me takes the small number and tries to do something useful with it. Okay, and as I said, the variable I play with is we take the water leaving radiance, that's my signal, so that's coming out in some particular direction, namely looking up to my satellite, and I normalize that by the downwelling plane irradiance, which is a measure of all the light that's coming down onto the sea surface, as would be measured by a flat plane detector there. So that's a typical thing that people use as their reflectance for doing ocean color remote sensing. Okay, so enough on definitions. Once again, you're probably familiar with this, but if not, the whole game of ocean color remote sensing got started by an instrument called the Coastal Zone Color Scanner, which was launched as a proof of concept thing back in '78. It was supposed to work for about 3 months and then it would probably die, and it worked for years and years and totally revolutionized the field. It only had 4 wavelength bands here, and the point here, the thing that got this game rolling was if you look at water leaving radiance as a function of chlorophyll concentration, if you look at if the low chlorophyll, so open ocean waters, that's the top curve here. The curve peaks into blue, that's very blue water. And as the chlorophyll concentration increases, so here's measure at 0.27, 0.24, blah, 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 down to about 9, that curve shifts to having its peak in the green. So people looked at this kind of data and they said, look, if we could put a sensor up there and measure, say, a blue wavelength and a green wavelength, and look at the blue to green ratio, so let's say the ratio of 443 to 550, then that changes systematically with the chlorophyll concentration. And so they literally had 33 data points to start this whole game off. And so you simply fit a curve to your 33 points, you get a nice little formula here, and then you can go along and measure the radiance at these 2 wavelengths, take the ratio, so we're normalizing out here, once again, the magnitude, and you'll come up with a nice little formula that'll give you chlorophyll. And those kind of formulas are good to kind of 30 to 50% area. And of course, since then, we've got a lot more data points. You can fit a fancier curve, but still the basis of operational ocean color remote sensing for things like MODIS and CWIFs is still plugging in numbers to very simple formulas and getting an answer that's, 30, 50%, and that's about the best you can do with that kind of thing. But it works, it's fast, and it's good enough for many purposes, but not all. And as I said, all of these pretty pictures that you see all come from applying a little formula like that, pixel by pixel, typically at about a kilometer resolution, but people just had no idea that the oceans had this kind of fine structure until they started doing satellite remote sensing. And, with a ship or a buoy, you get this point and you get that point, and maybe you get this track right here, and that's it. You really don't get the big picture. Okay, so to get on to the recent work then, which I've been doing this sort of thing for roughly 10 years, the point is we have a number of sensors up there that are multispectral. That means typically 5 or 10 wavelengths, typically bandwidths of about 5 or 10 nanometers. And people use these statistical algorithms or empirical algorithms to process that data. Those algorithms and those sensors work pretty well in open ocean, phytoplankton-dominated waters. The atmosphere is easy to deal with. It's a marine aerosol. Most of the aerosols are just sea salt. Life is good. when you try to apply these things to coastal waters, especially if you're on the east coast of, say, the US or China, the algorithms fail. First of all, the atmosphere is much more complicated. You have absorbing aerosols from things like soot from coal-fired power plants and air pollution of other kinds. That messes up the atmospheric correction problem. But also the water itself has a lot of minerals either coming off the land, that's resuspended sediment. You get pollutants from the land. If it's shallow water, you see the bottom, and then the bottom reflectance is a part of your signal. And all of those little formulas are just developed for infinitely deep water where there's no bottom signal. So all of a sudden, the statistical algorithms just don't work very well, or they totally fail. So in recent years then, people have developed what generally gets called physics-based or radiative-transfer-based algorithms. They're going to hyperspectral sensors, hyperspectral meaning I've got order of 100 wavelengths, typically about 5 nanometer bandwidths. So there's more information there than there is in 5 or so wavelengths, of course, and so you can expect to get more information back out. But also by building in some physics instead of just having fancy curve fitting, and of course the fancy curve fitting includes things like neural networks, but it's still just statistical curve fitting, you can get more information out by building in some physics to start. So who cares about this? Well, the Navy, for example, the reason they fund me is the Navy doesn't love coral reefs, but they don't like to run into coral reefs. So they need things like maps of bathymetry, that is water depth, and bottom classification. And they need those at kind of meter scale, maybe at worst 10 meter scale, preferably 1 meter scale. They need that for amphibious operations. They need maps of water clarity for diver operations, or if they're going to decide whether or not to fly, let's say, a mine-finding LiDAR system, they want to know, is it worth going out here and flying this thing today, or am I just not going to see anything because the water's too turbid? So if they can fly over, get an idea of how clear the water is, then they can decide, do I fly a 488 nanometer laser or a 532, or do I stay home, or do I keep the SEALs team at home, or do I send the SEAL team in? Those are the sort of things that the Navy's interested in. In the civilian side, the ecosystem managers need to know basically what's going on with my seagrass beds, my coral reefs, my mangroves, etc. And that's a management thing both for fisheries, for recreation, just for basic understanding what's going on in the ocean. You have episodic events like hurricanes where you'd like to be able to go out and map things beforehand, and then the hurricane comes along, you can run out the next week and see what changed. Or there's a harmful algal bloom, you'd like to monitor that at least daily. Satellites, you might get one view a week if it's not cloudy, but you'd like to be able to maybe monitor this harmful algal bloom that's bubbling around off the coast of Florida somewhere and messing up the beaches, and get a daily forecast on that. You can do that with aircraft pretty nicely. You can't do it with satellites. And of course then looking at long-term changes from global climate change, or a lot of problems in coastal waters come from changes in land usage. So now you've got a farm where you used to have a clear stream coming in, now it's putting in a lot of nutrients, and so you get algal blooms offshore. But anyway, for a lot of these purposes, you need kind of 1 to 10 meter spatial scales, not the kilometers that you get from something like MODIS, and you'd like to have often very quick turnaround on your imagery. You fly the airplane, and at most tomorrow morning, if not tonight, give me back an image of what's going on. So that's the kind of thing I'm working on. And I've developed a spectral matching and table lookup technique here, and I gave Rob a directory here with things like this paper in it if you guys want to look at that later. So anyway, what I'm going to do in this technique that I'll talk about now is I'm going to create a database of remote sensing reflectance spectra. And each one of those spectra, it's created by running, in my case, a a radiative transfer model called Hydrolite. And so for each spectrum in there, I know what the water absorbing and scattering properties are. I know what the bottom depth was. I know what the bottom material was, sand or seagrass or whatever, so the bottom reflectance. So I create this database. And so, for example, this is one that I created for the Bahamas. I have some general idea of what the water's like there. It's nice, pretty clear water usually. And it has a lot of what's called color-dissolved organic matter, CDOM, which actually comes from decaying vegetation on the bottom. But anyway, I know, I'm pretty certain that somewhere in this range of absorptions is in a particular image of the Bahamas, it'll be in that area. Now, if I went to Puget Sound, it'd look different. But for the Bahamas, I kind of have this range of absorptions. I have some range of scattering coefficients, some range of backscattering. So I'll take these for the water properties. I know from measurements that people go out and they measure reflectances of seagrasses and corals and sands and mud and so forth. So I just came up here from various sources with 123 different bottom reflectances. And those are things like clear sand up here or sand covered with biofilm, and the darkest ones down here are things like seagrass leaves. There's a lot of reflectances in here for corals. I can mix and match those and have 20% sand and 80% grass and 40-60 and 50-50 and so forth. So I just make up some bottom reflectances, and I'm pretty sure that any place I look in the Bahamas there, the bottom will be fairly well described by some one of these reflectances. And I've got a few reflectances in here like kelp, which I know don't occur in the Bahamas, but they're there as kind of a test to see if I go astray. And so yeah.
Model data?
These are actually measurements here.
That's empirical.
Yeah, so this is measurements where various people have gone out with in-water instruments, and you get right down about a centimeter from a coral or a seagrass leaf, you hit the button and you measure the reflectance.
And they have a GPS hanging off their back.
Yeah. Although in my case, I just need to know that, this particular species of coral here has this reflectance, and I don't care where it was measured. Okay, and then when I do my radiative transfer simulations to create this database, I'll take a set of water properties, I'll take a bottom reflectance, and I'll put that bottom at anywhere from a centimeter to 25, 50, maybe down to 15 meters, and then maybe every half a meter down to 20, and a couple of deeper depths, and then one where the water's infinitely deep. So basically, I'm going to take a number of sets of water properties times a bunch of bottom types times a bunch of depths, and for each combination there, I'll solve the radiative transfer equation, and this is for the sun at a particular location and a wind speed and atmospheric conditions and so on. So here for the Bahamas, I actually had like 25 sets of water properties, 123 bottoms, 83 depths, so that gives me about 250,000 remote sensing reflectance spectra. It's a one-time calculation, and I just keep adding to this database. If you give me some properties for Puget Sound, I'll just do some more calculations and I'll add Puget Sound kind of spectra to my database. Okay, and that in this case was about a week-long run on an old PC I had years ago. But I don't care how long it takes, it's a one-time calculation. So here's some of my remote sensing reflectance spectra. This is 1% of that database, and they're everything from very large magnitude spectra, which would be a bright sand bottom in a very shallow water, to very dark spectra, which would be things like a dark seagrass bottom in 10 or 20 meters of water. So anyway, the point is that for each one of these spectra, I can now look in my database and say what were the conditions that generated that spectrum. Okay, so now I've got my database. I want to go process an image. All right, so the background here is an image of the Bahamas. That's an island, and that's an island, and then here's a sandbank. Here's some mixed vegetation on the bottom, and there's coral reefs and such in here. So what I now do is I go to a particular pixel here, and I pull out the measured spectrum. Now the measured spectrum is coming from an airborne sensor called PHILS, which stands for Portable Low Light Imager, Portable Hyperspectral Imager for Low Light Spectroscopy. It's a little suitcase-sized imager built by the Naval Research Lab that they fly on airplanes, typically fly at about 10,000 feet. You typically get about 1 meter ground pixel size, depending on what lens you put on it and all of that. But basically, it then gives you a radiance measured at 10,000 feet. They do the atmospheric correction on that, give me the remote sensing reflectance after it's been atmospherically corrected. So that's what you see pulled out here. So right here at this pixel, there's the measured remote sensing reflectance atmospherically corrected. Okay, so I take this spectrum and I compare it with every spectrum in my database. Now I do that in an intelligent fashion, so it's actually a pretty quick process, but I simply search the database and I find the closest matching spectrum, which is the red one. So you can see the red and the green here are actually very close. And I guess I can turn down the lights here, make things a little more visible for you guys, however that works. Okay, so you can see I get a pretty good match. Then I take the red spectrum, that was number 87,085. I look in my database and say, what created that spectrum? Well, the radiative transfer calculations had the bottom at 2.75 meters. I had a mixture of 80% sand and 20% grass, and it was inherent optical property, that's water properties, set number 17, which had this absorption, this scattering, and that backscattering. So at that pixel, my retrieval is then water's 2 3/4 meters deep with a mixture of sand and grass, and here are the water properties. And then I simply go to the next pixel, search the database, and away I go. So it's a very simple conceptual thing, and works quite nicely. I'll make a point here. A lot of remote sensing algorithms just look at spectral shape. They're taking a band ratio or something similar. I'm relying on both shape and magnitude. I have accurately calibrated atmospherically corrected and radiometrically calibrated things. So if you ask the question, well, how does this guy tell the difference in deep water that's high chlorophyll and has a green spectrum with a point like this that's shallow water, but it has a green bottom, so it has a green spectrum? There's a potential ambiguity there. And the answer is they'll have the same spectrum shape, they'll both be green spectra, but they have much different magnitudes. The one that's reflecting off the green seagrass bottom will be low magnitude. The one that's in, say, open ocean, deep water, high chlorophyll will have a high magnitude because there's a lot of backscattering by the chlorophyll particles, the plankton particles, so that'll shift that spectrum up by as much as a factor of 10. So that removes the non-uniqueness. So I'm relying on good atmospheric correction. And this kind of technique fails if you have bad atmospheric correction, and of course those band ratio algorithms get around magnitude problems, but they fail for a problem like this. Okay, yes?
Is it possible to search your database for a given pixel and find, let's say, 5 different spectra?
It's coming.
Okay,
yeah.
I'll be quiet.
Okay, so here's an example. This is also in the Bahamas. Here's an island here, Lee Stocking Island. You just look at this image and you say, this looks like a bright sand bottom. And, well, here's some kind of vegetation on the bottom. I don't know what it is. And, well, here's something out here. Now, is that deep water or is it just a dark bottom? I'm not sure. And there's actually an area here called Horseshoe Reef that has a lot of corals in it. So this particular image, it was taken by this PHILS sensor by the Navy. This is about 500 by 900 pixels at about 1.3 meters resolution. Okay, so I come along with my data cube now that at each one of these pixels I have this hyperspectral reflectance, and I work my magic on that. And so here, the color part, is my retrieved depths, just bend in 2-meter bends for making a pretty picture. Then the Navy also went out before this experiment, and they went back and forth in a small boat for days with an acoustic pinger, getting acoustic bathymetry to use to ground truth the techniques like mine. So I have at each little point here an acoustic depth that I can compare with my retrieved depth. Okay, so if we make that comparison, here's the retrieved depth, here's the acoustic depth, and here's just a scatter plot where really most of the points are pretty close to the one-to-one line. So you can see, on average, I'm about 7.5% too shallow, or about 0.5 meter too shallow. But it's pretty good. These outlier points, which are terrible retrievals, it says, my retrieval said it was 2 meters deep and the water was really 10. Well, if you actually go back and look at those pixels, they're ones that are contaminated by sun glint or white caps. So my technique says, wow, I see a really bright spectrum, and the only way I can get that is if I have a shallow bottom with a bright sand bottom on it. So that's why it gives me a 2-meter retrieval here when it was really a 10 meters of water, but I had a white cap. Now, I could filter out the white caps, but and people normally do that in the open ocean by looking at the magnitude of the spectrum and saying, oh, this is way too bright, throw it out. If I do that sort of thing, I throw out all my really shallow waters from 1 meter or 2, because those are the ones that have really bright water-leaving radiances. So I chose just to leave the values in and realize that the errors in here include both things like white caps, and also the navigation system on the airplane failed this day. And so we just kind of have to eyeball warping the image and tying it to this island here and kind of hoping we're okay. But some of these points are where I actually had an acoustic ping that might have been in 6 meters of water, but there was a coral head right here 5 meters away that was 2 meters deep, and I've mismatched those. And so, okay, you know, that's life. The bottom line, if we plot this distribution, one's the acoustic and one's the lookup table technique, they're pretty good. And here's a couple of other ways of showing the same information. Here I've plotted the relative depths, retrieved minus acoustic over acoustic. You can see about 88% of these pixels, I was within plus or minus 25% of the correct depth. Now the Navy has a requirement that they say, I don't care how you got the depth, but we need to know it to within 25% for it to be useful. Well, I'm meeting their requirements 88% of the time on this particular image. So that's pretty good given the problems with the data set. Or about 70% of the time, I'm giving you the right depth to within plus or minus 1 meter in waters that go from out to about 15 meters deep. Yeah?
What is the distribution in the top right chart?
Oh, that's just how many pixels are there in half-meter thick depth bins.
It's a histogram.
Yeah, so and then normalized to 1. So basically there's a lot of pixels here that are about 5 meters deep. There's not too many that are 8, and then there's a bunch more pixels that are around 10 or 12 meters deep. So that's all that one was. So just different ways of looking at the retrievals. But the Navy looks at this and says, this is way better than no information at all, so we're happy. Here's the map of bottom classification, where at each pixel I simply color code what kind of bottom I retrieved there. And first of all, a lot of these red specks here, you trace those back and you actually look at the original image. Those are the white caps that are out here in the deeper water. There's pretty much none of those back in the shallow water because there's a little wall here. This is shallow, this is deeper, and the white caps have disappeared before they get in here. So I look at this and I say, well, you know, we looked at the original image. It looked like bright sand bottom. That's what I got. Some darker stuff. There's mixtures of vegetation of different kinds in here. Yeah, that's what I'm getting. That's probably right. The coral reef is right in here, and I'm getting a lot of red pixels here, which actually are corals. And then I'm getting these red and blue speckles out here, which are the white caps. But this big area here is actually seagrass, dense seagrass in waters that are about 10 meters deep. And in fact, that's what I'm getting. I just classified it as dense vegetation, and so that was pretty good. In my database, I had things like kelp. Well, that's a different looking kind of plant, and there was not a single pixel in here was retrieved with kelp. There was not a single depth here that was retrieved as being infinitely deep. So it's very reassuring that I'm not matching a spectrum that for some reason looked like kelp in a certain depth of water or whatever. So it's I don't have problems with non-uniqueness, and that was something that I worried about for a long time before I realized that by having well-matched or well-calibrated spectra, I remove the non-uniqueness problems. Okay, so to get to Rob's question here, the previous couple of retrievals, I simply found the closest matching spectrum. I looked at that to see what the conditions were. Well, of course, my measurements have little bits of noise in them. If we just back up here and, you know, you just look at this and say, there's little wiggles here. And, you know, if I had just a little bit of noise or imperfect atmospheric calibration, I would have matched a different spectrum in the database and gotten some kind of different retrieval. So rather than worry about am I noise dominated, let's keep, let's say, the closest fitting 30 or maybe 50 spectra in the database, and then look at what kind of distribution of environmental parameters do I get from several dozen closest matching spectra. So here, just for one pixel in that image, I've got the red curve is the measured spectrum, and these things tend to get noisy out here in the infrared because the signal's low. I've got the closest matching spectrum, which is a blue curve kind of on top of things. And then I've got also the next 29 closest matching spectra. And you can see they're all very close to the measurement. Any one of those would be a believable good match. But if we take these 30 closest matching spectra and look at the distribution of retrieved depths, well, for this pixel, here's what we got. They're all between about 10 and 13 meters. I never get one that's, 5 meters with some kind of weird bottom. So I'm pretty sure that regardless of which one of these is actually closest to reality, reality is somewhere around 10 or 13 meters depth. The closest matching spectrum actually gave me 11 meters, 11.37, after I corrected for the tides. The acoustic depth at this pixel was about 12.8. The closest was 11.4. If I take the average or the median of these spectra, I get about 12.4. So I'm getting a better retrieval by looking at a statistical distribution of my closest matching spectra and doing something like a median or an average. And then I can also now, what's very important, if I do this, I can say, okay, I think the water is about 12.4 meters deep with a standard deviation of maybe a meter. So I've been able to put some error bars on my retrieval, and that's really important. It's just telling the Navy that the water's 5 meters deep, but I don't know how big the error is. It leaves them worried. So if you can tell them it's 5 meters and I'm 90% confidence that it's somewhere between 4 and 6, that's fine. If I'm not confident of that, then they'll do something differently. The same 30 spectra here, if we look at the retrieved bottom reflectances, well, let's see, the closest match is the purple one. The most frequently retrieved is this red one. The average of the 30 is this one. And they're all very similar spectra. They all have this green, yellowish green peak here. They all have what's called the red edge, which kind of tells you it's some kind of chlorophyll bearing plant. And if you actually go back now in the database and say, what do all these spectra correspond to? Well, the most frequently retrieved one was 30% sand and 70% seagrass. These other ones were similar mixtures of either sand and grass or sand and sargassum or turf algae or some other similar looking plant, optically similar. And so I can be pretty certain that the bottom here is fairly dense vegetation, so some mixture of sand and vegetation, but mostly vegetation. It's probably seagrass. What the Navy is often interested in, is it sand, is it mud, is it rock, is it coral, is it seagrass? They don't care what species of seagrass or anything like that. Here with the same spectra, if we look at the retrieved absorptions, all 30 of those spectra have virtually identical absorptions. So I'm very confident that this is what the absorption of the water looks like at that pixel. Also fairly confident about this is what the scattering looks like. Here's the backscattering. It's very uncertain, you know, factor of 2 here in the blue. Well, what's going on here is I've got water that's basically 10 meters deep. I have to get sunlight down 10 meters, reflected off the bottom, back 10 meters and out. There's not much water column there to backscatter the light. So it really doesn't matter much what the backscatter of the water is doing. What matters is the absorption by the water and the reflectance off the bottom. So in this case, I can put error bars on things. I can tell you I'm pretty confident about absorption and scattering and what kind of bottom type it is. I can't tell you more than a factor of 2 or worse what kind of backscattering the water has. Now, if this were deep water, it's then backscattering that's important. And the bottom reflectance might be very uncertain. If I'm in, say, 30 meters of water, I'm almost not seeing any bottom at all. So that's the idea. Okay, so let's look to the future here, just to kind of recap. The world today that's out there now for NOAA and NASA and people like that are multispectral sensors and statistical algorithms. Plug in the number formulas and away you go. Those are still useful ways of doing things, but they've also reached their limits. You're never going to get better than this kind of 30% on chlorophyll and so forth from a statistical algorithm. And the reason is there's more than just chlorophyll determining a water leaving radiance. You have particle size distribution and physiological adaptation to the local nutrients in the light and so forth that also affect the optics, even though the chlorophyll is the same. So you kind of, you know, can't go any further with those kind of algorithms. Okay, the recent work that I've done, and also people in Australia and China and Estonia and all kinds of places, they've concluded that airborne hyperspectral sensors and these radiative-transfer-based algorithms like the spectrum matching, they do give you more information, and those algorithms, sensors, and software and so forth are now being transitioned to the operational Navy. And so what should be the next step for people like NOAA is to say, okay, you know, we now have these new techniques. We need to start putting up sensors that are making hyperspectral measurements. We need to do new ways of doing atmospheric correction using radiative transfer stuff, not plug in the formula kind of stuff that has worked in the open ocean but often fails elsewhere. So that's could be and should be, but isn't looking too promising for funding regions. Okay, so let's talk about computational issues for the future here. Here's a MODIS image of the Bahamas. So here's Florida, here's Cuba, here's the Bahamas. MODIS is a nominal 1 kilometer resolution. Well, let's say I want to do for all of the Bahamas, and you see all of these shallow waters here, and you've got sands, corals, seagrasses, anywhere that's looking the light blue, that's optically shallow water, typically from 1 to maybe 10 meters deep at the edge. Okay, we'd like to map all of this stuff, and my little image, if we look at this little area right here, here's this Lee Stocking Island area where I was working, and here's this image that I showed you a while ago rotated around. Here's the island, here's Horseshoe Reef. So here's my little image in this one, which is in this little area right here. Well, if I want to do for all of the Bahamas banks here, what I did for this particular area, I'm looking at about a factor of 200,000 just on the area. Okay, Let's say we want to map coral reefs all over the world. Well, here's a map of the distribution, the little orange spots of wherever there's a coral reef. So if I take all of the coral reefs in the world compared to the area of my image, well, that's something like a factor of 1,000,000. Now, if I wanted to do things where I go from, let's say, MODIS, which is at 1 kilometer resolution, and I wanted to do things at a 1 meter resolution, I'm looking at 1,000,000 more pixels that I have to process. You say, well, I don't know, I can't do that, but the coral reef people tell me we would just be overjoyed if we could map coral reefs at 10 meter resolution. That's about, because most of these coral reefs have never been mapped at all. And I don't know the latest numbers, but 10 years ago, here's the Great Barrier Reef in Australia. 10 years ago, 60% of the Great Barrier Reef was still using nautical charts made by Captain Cook. And the charts just say, danger, coral reefs in this area. And if you remember, about a year ago, there was I think it was an iron ore ship came out of Brisbane, I think it was, heading up to China and ran aground on a coral reef here. I mean, that's how bad it is. So anyway, the coral reef people say we would give anything if we had a map of the world's coral reefs at 10 meter resolution. Well, okay, going from MODIS to 10 meters, that's still a factor of 10,000. So we're looking spatially at enormously more data processing, factors of 10,000 to millions, depending on what you're doing. If you look at the wavelength issues, well, MODIS has 36 bands, of which 9 are in the visible, and the other bands are used for atmospheric correction and other purposes. There's a proposed satellite called hyperspectral and infrared imager. It's going to have 60 meter resolution, and it's got 210 bands from 400 to 2500 nanometers and about 30 bands in the visible. Well, if you just take the 210 Hysperi bands and the 36 MODIS bands, you're looking at about 6 times as many wavelengths we have to play around with. So that's an increase in the computation. And if we look at what kind of a database would I need to do my spectrum matching on a kind of global scale? Well, you know, for this one little Bahamas area where I had some idea of what the water was like, you know, I had 25 sets of water properties, and, you know, it was good enough. If I want to cover all the world's water types, from the Bahamas to Puget Sound to Monterey Bay to, you know, Antarctica to, you know, wherever it happens to be, coastal China, I don't know, I might need 1,000 combinations of water properties, because chlorophyll alone varies by, you know, a factor of 1,000 from like 0.01 up to 20 or so just in regular ocean water. And then you've got all the mineral particles to mix in, all the dissolved substances to mix in, and all different combinations. So, you know, you could easily say I'd need 1,000 different sets of water properties. And then I would say, well, how many bottom types do I need? I had 123 here in the Bahamas, and now I'm going to throw in whatever it is that grows in coastal China water and whatever it is that grows in Puget Sound. And I want to have this kind of mud and that kind of mud and this kind of rock and that kind of rock. So I don't know, just wild guess, maybe I need 500 bottom spectra, including combinations of mixtures of sand and coral and rock and, you know, whatever else is out there. I'm probably okay with the depth resolution I have, which was 25 centimeter spacing down to 15 meters and then half a meter after that. That seems to be good enough for almost anybody's purpose. And if you go to, you know, 1 centimeter resolution, well, pretty soon you're below the, you know, the digital count of your sensor. So anyway, that's okay. But if you just multiply this out, well, 1,000 IOPs, 500 bottoms, 100 depths, we're talking about 50 million spectra, and I had 250,000 in my Bahamas database. So I'm going to have a database that's at least a couple hundred times bigger, so it's going to take me a couple hundred times longer to do my search per pixel. Okay, so if we say, well, let's map the global coral reefs, like the coral reef people would like to have? Well, we could say, okay, I showed you here a while ago, I'm going to have something like 1 million times the area of all the coral reefs versus my little image that I showed you in the Bahamas. Now, I was doing my image at about 1 meter resolution. Maybe we can get by with 10 meters, so that's a factor of 0.01 that I get to multiply in there. Wavelength resolution, let's do it hyperspectral, so that's about the same. The database is maybe going to have to be a couple hundred times bigger or 100, whatever. So I'm looking at a total computational increase here of order of 1 million. And that's assuming, of course, that somebody's going to go out and fly around in an airplane and get the data. Now, for my Bahamas image, I can process that image in less than an hour. It's kind of 20 minutes to an hour, depends on which image I'm working with. But if I take an hour times a couple of million, now I'm looking at a couple of centuries for database, for image processing. Okay, that slows me down a little. If we say, let's just map the globe, but we're going to use this high-spatial sensor instead of the MODIS sensor. Well, now we're still mapping the world in each case, so no spatial difference. But the spatial resolution has gone from 1 kilometer for MODIS to 60 meters for high-spatial. So it's a factor of 278. Well, I've got MODIS number of wavelengths to high-spatial number of wavelengths, kind of a factor of 6. And then to really use high-spatial, we don't want to just, we've spent all this effort to get a hyperspectral satellite with well-calibrated remote sensing reflectances. Let's don't throw all that information out with a band ratio algorithm. We need to do some kind of spectral matching thing or something else. And so my technique, even though I can process several hundred pixels a second to do the spectrum matching, that's still way slower by at least orders of magnitude than just taking a couple of wavelengths, plugging in a formula and, getting a number back. So there's at least a factor of 100 more just for the processing of each pixel. And so pretty soon you have, 278 times 6 times 100 was 170,000. Well, processing the MODIS data is a full-time job for several people at NASA. They have this thing called the Ocean Biology Processing Group, and their whole life is processing MODIS and CWIFS data, and then somebody comes along with a slightly better algorithm and they reprocess all the data, and then somebody comes along with a better atmospheric correction, so they reprocess all the data to get a slightly better thing. Well, now we're going to have a full-time job for several people for several hundred, 170,000 times several people. Okay, well, that's not in NASA's budget, I'll tell you. So anyway, let's finish up now with talking about the atmospheric correction business. The game we play now is you measure this top of the atmosphere radiance. You kind of go through a multi-step process. You figure out what the sea level pressure was, which maybe is from a meteorological forecast program or maybe a different satellite that gives you that. You try to subtract out the Rayleigh scattering part. You mess around, get the ozone part. You try to get a water vapor profile and subtract that out. And you finally are kind of left with the aerosols, and you finagle around with some very approximate algorithms and try to correct for the aerosols. And you finally come up with a water leaving radiance. Well, here's a couple of examples numerically generated. Here's one where this is for a tropical location, latitude 0, spring, and I've got the same water properties. I had chlorophyll concentration of 0.3 milligrams per cubic meter. I had a 50% sand, 50% coral bottom at 5 meters depth. So that's my water. And then the difference is this is for the high-spatial sensor. I'm on their design team for part of this. One of them was, we're looking straight down at the ocean. The sun's over here somewhere. We look a little bit to the east or we look a little bit to the west. Now, one of those is going to pick up a little more sun glint than the other one. It's going to have a slightly different atmospheric path length. So we actually get the two curves here. One of them, this top of the atmosphere reflectance here for One of them, let's see, east is looking solid and west is the dotted. So here's our two top of the atmosphere curves that I measure for two slightly different viewing directions. The atmospheric part is about the same. The water leaving part, the green, is identical. What's different in these cases are the amounts of surface glint, because I was looking sort of towards the sun and a little bit away. So one of them picks up more surface glint. Here's a simulation where I have the same atmosphere, the same viewing direction, but I have two different water types. So one of them, I had a chlorophyll of 0.3, and it was shallow water with some coral bottom or whatever. And then I had a chlorophyll of 5, and it was deep water. So here's my deep water spectrum. Here's my shallow water with maybe it was a grass bottom. So the water's different. The surface glint is the same. It's the same viewing direction. The atmospheric path radiance is the same because that's all the same. But I get a much different top of the atmosphere radiance because I have much different water leaving radiances. So then I come along and say, well, you know, if you just give me the water leaving part and I do this spectrum matching business, it works really great. But I've had to do this multi-step process to get from this curve down to this one or this one. How about we do the spectrum matching at the top of the atmosphere? And then my database is going to have both ocean and atmospheric properties in it. So the Navy's actually developed a technique for that they call Toth Cup. And what they did was they said this was for correcting airborne imagery, but it's now also being used for top of the atmosphere. They say, okay, I've got, you know, all these different sun angles, all the different viewing directions of my sensor looking at the ocean, different altitudes the sensor can fly at. I've got different aerosol types, different humidities, different wind speeds. When the wind speed, of course, changes the sun glint because it changes the waves on the surface. So you kind of think of, you know, viewing geometry times different water vapor profiles times different aerosol types times different sea level pressure times different sun angle, etc. And they end up with 63 million different combinations. So they did this multi-month long, extremely computationally intensive, basically database generation, just like I did. They've got 63 million atmospheric spectra. So what they do is they come along and they say, well, I'm flying along here today and it's, you know, 80 degrees at the sea surface and, you know, the winds are 5 meters per second and I'm looking in this direction and the sun's in that direction. So I go in my database and I pick the number here out of the 63 million that corresponds to this sun, this viewing direction, this water vapor profile, this wind speed, this aerosol type, and then I take that spectrum and subtract out of the measured one to get the water leaving radiance. Okay, so that's what they're doing there, and my imagery is largely corrected by doing that. Okay, so what I'm thinking is we now do the same thing, except I'm going to have a database with 63 million atmospheric conditions times my 2 million sets of water properties, so that when I match a top of the atmosphere spectrum, it's going to look through the database of atmospheric and oceanic properties, find the best fit, and I basically retrieve atmospheric properties and oceanic properties all at once. Now, that sounds like, you know, it's almost an impossible thing to do, but we're already doing that anyway. The difference in this spectrum and this one and this one and this one is just atmospheric and oceanic conditions. So I'm starting with the same information. It's just now we do a two-step process, correct for the atmosphere and then retrieve for the ocean. There's the potential there to do it as a one-step process. We simply find which atmospheric and oceanic set of conditions would best match a particular top of the atmosphere spectrum. It's just a much bigger database and a much bigger search process. And people have thought about this, but nobody's really studied it in any detail. Okay, so, and part of the reason is, you know, they're too busy worrying about just getting some numbers out of MODIS without going off and getting on these tangents. And it's so computationally intensive that people have said, I think we ought to look at this, but nobody's looked at it.
Correctly, it's 100 trillion spectra. You multiply the 63 million times.
Yeah, it's a big number, whatever it is. Yeah, and of course, in all honesty, you really want to do things intelligently by saying, look, I'm flying over the tropics here. I know I don't have an Arctic Ocean atmosphere, so we immediately call the database to tropic summer or Arctic winter or mid-latitude March or whatever, and cut the computation by orders of magnitude doing that. But just as a brute force view of things, that's the kind of numbers you're looking at. Okay, so to finish up here, this world of multispectral sensors and statistical algorithms, I personally think has been milked for about all it's worth, although the current and the next generation of operational sensors like the VIIRS sensor, it's once again another multispectral and using the same modus algorithms as before. Well, that's better than nothing, but it could be better. People like me have developed these new techniques that give nice results. I just also comment here that, well, we get, not gigabytes, but terabytes and bigger data sets now when you're flying a sensor that's getting imagery at meter or 10 meter scales instead of kilometer scales, and you're getting 150 wavelengths instead of 8. Well, all of a sudden you've got a real database, just a management problem. What do you do with all this data, and how do you manage it and find what you want? And in conjunction with people like me developing retrieval algorithms, other people have developed the whole software side of managing the data sets and so forth. And like there was a company here called Weojio that's in Portland, Oregon. I've worked with those guys on all this Bahamas stuff, and they funded or they developed the software for the image management, and you've got ground truth that you want to tie into an image, et cetera. It's the whole GIS thing. So that's a good company. Go to their website, and they actually, the basic scientists who were doing this work with me, they spun off this Weojio company just to commercialize all of this image processing and image management stuff that they had to develop in order to handle the data we were collecting. So anyway, just throw that in there as a reference. You guys might be interested in seeing what they're up to. So yeah, there's big computational problems. They're not insurmountable if you do things intelligently. The real problems in all of this for the next, decade or so is really financial. The Navy has been very generous in funding me for the last decade to develop this kind of stuff. I've kind of solved their problem now, and the work I've done is being transitioned now to the operational Navy. And other people have done, lots of other things. Financially, the Office of Naval Research next year is going to close down their environmental optics program purely for financial reasons. I mean, the Navy's spending their money on, wars in Iraq and things like that, not on basic science. Basic science is expendable. NASA and NOAA are under severe pressure to cut budgets, not to do fancier things for coral reefs with hyperspectral at 10 meters, etc. So, NOAA's just recently told that probably the best they can hope for next year is to go back to the 2008 level of funding. So everybody in DC is hurting for money big time. The people who are not hurting for money, of course, are the People's Republic of China. I go over there quite a bit. I teach classes in China and, give them these kind of talks. And when I was at the Chinese Academy of Science, they have a thing called CODE, Center for Earth Observation and Digital Earth in Beijing. So I give them a talk kind of like this. And then they said, well, we're developing all of these hyperspectral remote sensing sensors, and they showed me all their stuff. They've got like 20 people just at this one location. They're developing their own hyperspectral sensors, their own atmospheric correction stuff, because the Navy's not going to give them Toth Cup, for example. They have 2 airplanes that are nice looking, spiffy airplanes like, Microsoft executives would fly around on. And this whole team of people just acquiring data, processing it, mapping their inland and coastal waters. And they told me that this was now 2 years ago. They said they had flown over 10,000 sorties with their airplanes mapping Chinese inland and coastal waters. To put it in perspective over here, the fellows at the Florida Environmental Research Institute, which are the ones that spun off this Weojio company, they had a big contract with the state of Florida about 3 years ago. And Florida said, wow, this is great. We want to map all of the Florida waters, all of our seagrass beds, coral reefs, et cetera. We're going to do that at 1 meter scale, and you guys are, the state of the art, and here's the contract. And just as the airplane was taxiing down the runway, the economic fiasco happened on Wall Street, and Florida said, whoa, man, science is a luxury. Cancel the contract. We're just going to have to do without knowing where our coral reefs and seagrass beds are. So anyway, I was told by one person that China is spending roughly $1 billion a year on hyperspectral airborne imaging, including sensors, systems, airplanes, the whole 9 yards. Over here, if I'm a scientist and I want to fly a system to, let's say, go to Puget Sound for a couple of weeks and fly around and get imagery. I mean, it's a major process to get something like the Avarice system or the Navy to come out here, and you plan for 2 years ahead of time, and then they block out this 1 week for you, and then it's cloudy, and well, I'm sorry, we can't come, and it's almost impossible. Then when I was in Qingdao this summer teaching a class with Emmanuel Boss, and we said, well, suppose you want to do a field experiment off the coast here, and you want to, you're going to have a ship out there, you're going to have a buoy or something, and you'd like to have one of your airplanes come over and get hyperspectral imagery. Is that easy, or do you have to get funding for that, or how does that work? And he said, just make a phone call. Just tell them to come, that's it. So much different view of how science is funded, and if you have an almost unlimited amount of money versus dwindling money for discretionary things. Okay, so that's my story. I hope it was useful and interesting, and in a way I've put myself out of business with the Navy because I developed this stuff, it works, and they're happy, and now I need to, it's time for me to retire and go kayaking, and I'm not unhappy with that. But anyway, that's the sort of thing that I do, and kind of gives you guys an idea of the computational aspects of where we would be if we actually had the money to fly these kind of sensors and do what the scientists and the land managers or the ecosystem managers, what they would like. The problem, of course, is acquiring the data. And so, there's, of course, it's not totally grim, but a lot of the systems that have been developed over here are basically, they're in mothballs right now because there's not enough money to fly them. The Australians, on the other hand, like the Chinese, they are very big on hyperspectral remote sensing of their waters because they're tired of running into the Great Barrier Reef because Captain Cook's chart was a little bit low resolution. So they've got a big program down there that's flying hyperspectral airborne sensors all over Australia all the time. And a lot of the European countries do this as well, and the Baltic and of course off the Atlantic waters there, because they've got big pollution problems from just human usage of the land areas and the waters. Places like the Netherlands, they fly these kind of sensors over their lakes because the lakes are the drinking water. And I've seen spectra and data from Dutch lakes where the chlorophyll was 1,000. I mean, you could almost walk on the water. And so what they're interested in is being able to fly over a lake, look at it and say, phytoplankton bloom underway here. We're going to have to shut down our water treatment plant for the next month and get the water from somewhere else. And that's much cheaper to do by flying a sensor say, once a week than it is by trying to go out and go around in a boat up and down all over some lake. Same thing in China. They have some pretty big reservoirs there that they like to monitor on a routine basis just to see what the water quality parameters are, because it's drinking water for them. Or, of course, off the coast, it was a big embarrassment for China during the Olympics when they had these incredible algal blooms off of Qingdao there, and they literally had to bring out the People's Liberation Army and, scoop up algae by the, truckloads for weeks just to so you could run a sailboat through it. So they're very interested in monitoring those kinds of things, understanding what's going on, and in many of those cases, it's nutrients running off from the land that are causing the algal blooms. So anyway, other people are interested in it, and my kind of world for the next year, as I'm wrapping up a bunch of papers on some of the stuff you saw here, and transitioning my software to the operational Navy and writing them users guides and going down and training guys on which button to hit to, read in an image, click here, process it, and you'll get out a map of the bathymetry and some error bars. So anyway, that's it. I hope that was useful, and I'm happy to hang around and answer questions.
Great. Thank you very much. So we'll just throw questions at you until you get fed up and leave.
Sure.
Or at least I will. The financial proposition of what you get out of flying these instruments versus the cost of building them and flying them, do you see that process, that thought process going on in the U.S.?
No. I could talk for ages. Let's say we're talking about millions of dollars here. NASA can find $100 billion for the International Space Station. They can't find, 100 million to launch a hyperspectral high-resolution sensor. And of course, I don't have a lobbyist in DC. Northrop Grumman and Boeing and those guys have lobbyists. So the money always goes into some big splashy showy thing like the space shuttle or the International Space Station, or whatever it is. And then by the time all of that's sucked off the top, what finally gets down to the NASA programs that do this kind of stuff, it's, well, you're going to get a 30% budget cut this year. And that's what happened at ONR. I used to manage that program 20 years ago at ONR. And for the last 10 years, ONR, and that's basically the Navy's funding agency for doing basic research. And it's, funds many different kinds of things, not just oceanography. They basically took 30% a year budget cuts for year after year under Bush, because he was desperate to find some place to save a dollar to finance my unfunded wars and my tax cuts. And so something like science, well, if we can cut ONR from, I think when I was there, they had about a $300 million budget. Well, heck, let's cut them down to 250 and we'll save $50 million. And then that's like 6 hours of Iraq. So anyway, those kind of cuts have just gone year after year. Obama, of course, would be very favorable to science, but he doesn't have any money to spend. So anyway, there's the cost benefit part is never done. Nobody ever says that for, $50 million, we could map everything imaginable in coastal waters and monitor it and, so on and so on. And that's, 1/10 of 1% of what we're spending on something like the space shuttle. I mean, I always point out to people that just to gas up the space shuttle is $500 million. Nothing to do with what you're launching on it or anything. Just the launch fees are $500 million. And of course, I realize you do away with the space shuttle, all of a sudden you have 10,000 Lockheed employees unemployed. So that's why it's not going to happen. And whereas if you shut down basic science, you've got 100 people like me that are out looking for something else to do. So anyway, no, there's really not any rational cost benefit sort of thing. And, part of the problem here is, I got a phone call, to put it in perspective, got a phone call from a guy with the Houston Environmental Protection Office or agency, whatever it calls. He calls me up and he says, Kurt, I was reading one of your papers and, could you fly one of these sensors like up and down the Houston ship channel and, detect things like pollution? And I said, oh yeah, no problem. You put oil on the water and we could fly this sensor and I could tell you exactly what's going on and where it's coming from and what kind of pollutant it is and all of this. And it'd be just what you wanted. He said, man, if I were to do that, I wouldn't get out of my office alive today. The last thing that he can afford to do is fly a sensor like this and say, oh, look, the Texaco refinery is dumping whatever into the Houston ship channel. And, that's the way the world works. And so, yeah, there's a lot of problems out there that are easily solved for orders of millions of dollars, not tens of billions. And, I don't know if you're familiar with the whole NPOES VIIRS system. See, the CWIF satellite was launched in 97, I think it was, with a 5-year lifetime.
Is it still flying?
It's still flying. It's going to die any day. The optical sensor is working fine. All the gyroscopes and motors and such are on their backup systems, and all we have to do is when one of those fails, then it's gone. MODIS is also far beyond its design life. Now, there was this NPOES, National Polar Environmental Orbiting Satellite System, built by Northrop Grumman and various other people. So there's a sensor on that, VIIRS, the visible infrared, visible whatever, imaging spectrometer. That was going to be the replacement for CWIFs and MODIS. It was supposed to launch in 2006, and this was like, a $3 billion program. Well, it still hasn't launched. Maybe next year. It's finally a $15 billion program, completely sucking up every bit of money that NASA and NOAA and DOD could dig up for this. I mean, it's a complete fiasco. I'm actually on a National Academy of Sciences panel right now that's looking at the options for NASA and NOAA to keep the ocean color business going if CWIFs and MODIS fail. And in all honesty, the best answer is buy the information from China and India and Korea. Now, of course, they're not going to sell it to us, but we know, if life is good, the VIIRS sensor, first one will get launched the end of next year. MODIS and CWIFs will continue long enough that we can have some overlap between the sensors, because the real issue is here, if one dies and the next one starts a year later, you don't have this overlap to compare their numbers. And so that's a real problem. And so we're basically putting out a big, a big nested if statement for NASA and NOAA that says, well, if this happens, do this. If this happens, do that. If whatever else happens, you need to talk to the Indians and the Koreans, because all these other countries, China, India, the Europeans with MIRIS, for example, they all have ocean color satellites. Now, the Indian one, for example, the reason they put that up there was to look at Indian waters in the Indian Ocean for purposes like fisheries, because fish like to hang out where there are strong gradients in temperature and chlorophyll and so forth. The Chinese have theirs, and their real interest, of course, is looking at Chinese coastal waters, and the Koreans are doing the same thing, and the Europeans are doing the same thing. So some of those places like China, for example, of course, are very secretive about their results. They won't give you the results, and we don't give a lot of our info to China. There's all kinds of ITAR restrictions on the technology and all of that. The Indians always say, well, we're not ready to release the data. We kind of need to calibrate things some more. So you never get anything out of them. The Japanese tend to be fairly open, and so the Japanese ocean color sensors may, if CWIFs and MODIS fail today, they would be what keeps this game going. The Japanese and the Europeans with the MIRIS sensor would at least keep the climate data records continuous, although, the agreements are not often in place, but the science potential is there. So, yeah, a lot of countries realize the value of this, and the U.S. is basically dropping out of the game in many areas because we simply can't afford it. And for what went to bail out AIG, $60-80 billion there, I could do an awful lot of image processing for, let's say, just $1 billion, and then they could spend $79 billion on AIG. But that's not the way the system works here. So
to do just the image capture of an area, the device is already available?
Yeah, there are commercial instruments, CASI, Compact Airborne Spectrographic Imager, I think. It's made by a Canadian company called ITRIS, or I could send you the link. Anyway, CASI is a commercial instrument. It's like the size of a suitcase. You can buy various, models of it. That's what the Australians use. The Europeans fly CASI a lot. And
Is that a better instrument than the fills that you talked about?
I think it doesn't quite have the wavelength coverage down at the 400 nanometer area, and I've used some CASI data from Australia, and basically I had about maybe 30 wavelengths I was working with. With fills I have like 128, but it's good enough. And so a lot of people use CASI because it's there, it's a commercial off-the-shelf product. The Navy kind of started this game with the fill system back, they were developing that in the 1990s, and then it was really flying in like the last 10 years, and then there's been a couple of later versions of fills. So the Navy flies the fill system for their own purposes. There was a sort of son of fills called Samson, and it was the one that we were going to fly over coastal Florida waters. And it was, once again, it's better radiometry, better sensors, better everything, building on all the things that were learned from the fill system. And then when Florida canceled that contract, the people at the Florida Environmental Research Institute, who had developed the Samson sensor and then all this database management stuff, and that was a group of about 15 or so people, they kind of said, the handwriting's on the wall here a couple of years ago, and they actually sold that sensor, Samson sensor, off to Northrop Grumman, who flies it for the military. So, and it was used a fair amount in coastal California waters to map things like kelp beds, kelp forests, which are of great interest for recreation and fisheries and so forth. So then, of course, the Chinese have their own sensors for airborne work. So, yeah, I would guess the most commonly used sensor is CASI. And I can send you the links if you just Google or Bing, whatever you guys do here. I guess you're not allowed to use Google probably, but do an internet search on CASI, and you'll come up with CASI. Yeah. Incidentally, I got to tell you while I'm here, I really like Windows 7.
Oh, yeah?
It is sweet, yeah. So I haven't figured out where you've hidden all the buttons yet, but that'll come with time. But it is nice.
So let's just, I'm just curious, if you were to decide to do a single run over, let's say, southern part of Puget Sound, and so what kind of a check would you be writing to get?
I'd have to talk to the aircraft people. I would say just get the airplane here, do the flights. So you've got, and you'd want to, if you were doing it here, it'd be nice to send out some people in small boats and get some ground truth data, just to play around with. You're probably looking at, let's say, a few $100,000. You'd have, an airplane and 10 people hanging around for a week, and I know the Navy has come out and done some stuff here. This was the Naval Research Lab with their FILS thing. They have flown around parts of Puget Sound just kind of checking things out. But, I just do a back of the envelope calculation. You're going to have aircraft costs at, $10,000 a day or whatever that comes to. You're going to have, 10 people doing that for, let's say, a week. And, you could get the data for probably a couple 100,000. I'm just guessing. And then you kind of have somebody like me that sits around and processes the data. So yeah, throw in another $100,000 or something there. So you're looking at, $500,000, probably. And of course, once you get the airplane, the fixed costs are, get the airplane out here for wherever. And then if you want to stay around a second week, the incremental costs are not that much. It's a week of salary. And you could map Puget Sound probably at meter scale. When this thing, like the FILS system flies, let's say nominal 10,000 feet, and it's got 1,000 pixels across. It's a 2D CCD array thing where you have, when it's looking down, it's looking through a prism basically, and it spreads the light out with the prism in one direction. So you get the wavelength information on one direction of the CCD array, and then there's a lens that spreads it out the spatial direction, the other thing, and then you go picture, 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 and build up the 3D array. So each image, I don't know what the scan or the image acquisition rate is, but let's say 10 times a second, this thing is getting an image as it flies along. And so you're getting this 1,000 pixels across and 1,000 pixels in wavelength, and then they bend that on the chip to 256 wavelengths just to cut the noise down. And then I'm only interested in like 100 or so wavelengths from say 400 out to 750 because that's what I can see the bottom with. And so that's the way it works. And, I could come up with numbers like that if you're interested.
I was curious order of magnitude.
Let's say the $1 million. It's not a $10 million thing. It's the $1 million, and it's not $100,000. Right. Yeah.
And the swath, I'm inferring the swath is about 1,200 meters.
The swath is basically, nominal kilometer wide. So you fly up and down Puget Sound, and you want to have some overlap, of course. So let's say you cover Puget Sound at half a kilometer swaths, and you can image the whole sound in 3 days probably. And that's what we did. If you look, let's say if we go back to see which one here. I know where I want to go. If we look at this image here, you can see here are the swaths of this image. So here's one, here's one, here's one, here's one. So this is 1, 2, 3, 4, 5, and that's probably about 15 minutes or something, flying up, turn around, fly back, turn around, fly back. So that's how you build it up. And that's, once again, this is basically maybe 600, 700 meters. This was 500 pixels at 1.3. So roughly half a kilometer image here. That's, I've pulled out of one of these bigger paths here. So that's the kind of magnitude of things. There was actually a big field experiment called COBOP, Coastal Benthic Optical Properties Program, funded by the Office of Naval Research back in the early 90s. So the reason for that program was a 5-year program. The Navy said, we're really interested in figuring out how do we do this kind of stuff. So they had a bunch of people out there. It was about maybe 30 of us funded on this COBOP experiment for 3 different years. A lot of people went around and they did things like measure reflectances of all kinds of different sands and corals and such, and that's where I got those data. They had the FILS people with the very first version of FILS flying back and forth and getting the imagery. They had people running around in small boats getting bathymetry to check. They had people going around, divers getting bottom samples here and there, all that kind of stuff. And the purpose of that was to understand how the bottom in shallow waters affected the water leaving radiance, so that we could develop algorithms like my spectral matching or something else that would enable them to take this kind of image and retrieve bathymetry and bottom type. So, I could take all of this imagery here and process all of that in, a couple of days of time at most.
Right, and there's not a lot of rivers here, so you imagine that if you were to go to a coastal environment where you had a big influence from effluent, it would be a whole other dimension to the problem.
Right, yeah. This is interesting. You have all of these shallows here with all of this seagrass on the bottom. Now that's white sand there. But these greenish areas are mostly seagrasses, and then these areas like this, a lot of that are coral reefs. And so this is, the water is very high in CDOM, colored dissolved organic matter. Now, normally, if you go in Puget Sound, that water's high on CDOM as well. CDOM comes from decayed vegetation. In Puget Sound, it's land vegetation that decays and goes into the water via the rivers. Here, it's the seagrasses and the corals and other vegetation on the bottom that decays and goes into the water column. So what happens is they're very, this is shallow here. This is only a few meters deep, and then this is deep out here. So when the tide comes in, it brings in this clear, open ocean water, and there's very low absorption. Then the tide goes out, and all of the shallows drain out, and they've been sitting there cooking in the sun and getting a lot of very high absorption stuff in the water. And so then if you're sitting, let's say right here, depending on whether the tide has gone out or come in, the water is either very highly absorbing or very low absorbing, because it's either offshore water or it's water out of these shallows. And see right here, there's this huge area of shallows back here, and the tides go back and forth kind of like that. So open ocean shallows, open ocean shallows. So it's a pretty complicated environment. On the other hand, there's almost no particles in the water. You go to Puget Sound, there's a huge particle load from both sediments resuspended by the strong tides, but also it's, all the ground up glacial flour coming down the Nisqually Delta and down the Skagit and all of that. So it's a totally different area. And, and the chlorophylls out here tend to be sort of 5, whereas here, the chlorophylls are like 0.1. It's a totally different kind of water body. And this is shallow enough. You can pretty well walk from Lee Stocking Island up to, around the corner and up to Nassau. It's nice snorkeling.
Yeah, it seems like the characterization problem, you sort of have to start out with what kind of workforce or budget you have, because the full complete workup is, like you're saying, 30 people for 3 years or something like that.
Yeah.
And that's the kind of resource that's not likely to become available, so you have to scale back what you're doing to...
Yeah, that's why this has all been kind of piecemeal stuff. The Australians have gotten very good funding for doing their coastal waters. The Chinese have plenty. And then the U.S., during the last 10 years, we've had good funding for a lot of this work. And then just when the science got done and we're ready to really get operational, that's kind of when the funding vanished a couple years ago. So, the coral reef people, for example, one of the main applications of this high-spatial sensor is, well, they need 10 meters, but they only have 1 kilometer now. At least high-spatial would give them 60 meters. So you can't really identify, here's a coral head, and there's sand, and there's another coral head. But they can at least kind of get ecosystem level information like here's a coral reef area of Florida or Hawaii or Tahiti or wherever, that in this general area, I mean, it's kind of like looking at this image here. This is 1 kilometer data, but you'd have this kind of data on a 60-meter resolution, and that's a whole lot better than a kilometer. So, you know, but once again, even though I'm on this Hysperi, one of their little design teams, they're just saying, you know, you guys go ahead and do your design work, but we don't know about the budget at NASA headquarters. You know, it's so uncertain. And, you know, I've got a proposal into NASA that was sent off last March. It was called Theory of Remote Sensing, and had a bunch of stuff in that. Well, to put it in perspective, they got 120 proposals from that one Theory of Remote Sensing call. They announced that they would have money for 5 to 10. So right there, you're looking at a 10% chance. And now, when I talked to the program manager a couple of weeks ago, she said, we haven't even looked at the proposals yet because we don't know what's going to happen in DC when the new Congress takes effect. So, you know, maybe by the end of the year, we'll look at the proposals. But in all honesty, we're probably not even going to look at these proposals till at least February, because everybody's working on a continuing resolution for the budget now. And of course, the new Congress is going to say, science, that's discretionary spending, cut it. And we're really afraid it's going to come back and tell us something about global climate change, and we don't want to hear that anyway. So yeah, I'm pretty pessimistic about the U.S. Science game for the next decade. And if my Chinese were a little better and I was, you know, I might just move to China, because every time you go over there, you get 3 job offers. But you know, the people are great. The government's not so good. But if you wanted to do remote sensing, well, that's the place to be. So anyway.
Cool. Well, did you want to dig into anything further here? Or
Yeah, I just had a technical question about, you showed this image of the classification result that seemed to be relatively noisy. You had all these speckles and dots that kind of
that one,
visible.
That one.
So have you thought about doing anything like image processing to filter out some of this, and also do the same thing for the depth measurement?
Yeah, one of the things I'm going to be doing next year is trying to figure out a good algorithm where I can, you know, go into this pixel here and say, okay, here's my spectrum, and if you pull that out and look at it, it's really high in the infrared. So that's kind of telling you something's wrong. You know, infrared meaning 700 to 750. So you kind of say, oh, okay, I know that pixel there is way too bright, and if it's out here, it's way too bright because it's got sun glint or a white cap in it. So I ought to throw that one out. And people have those kind of algorithms. If you apply them to that image, you end up throwing out all of this as well, where it's really shallow, because those are also very bright at the near infrared, but they're bright because of the sand bottom. So I'm going to see if I can come up with some rational way to distinguish between a bright spectrum that's a shallow bottom versus a bright spectrum that's a white cap. And there's a bunch of people have tried that. Nothing works very well, because most of those people work in the deep water world, and those algorithms work fine. And so that's something I'm going to take another look at. I haven't really played with it much. But for this image, I said, you know, I'm just going to not worry about it, leave it in there. It's a crappy image, and let's see how good we can do with the crappy image, because sometimes that's all you have. And, you know, if you give me a perfectly corrected, atmospheric corrected image here, I can give you almost perfect retrievals, but you're always going to have some kind of problems. You know, the atmospheric correction was bad, the radiometric calibration was bad, you know, the white caps were not properly removed or whatever. So it's kind of worthwhile to take the worst case and work with that, and then I can go to the Navy and say, this is probably the worst image you guys are ever going to have, and I'm still meeting your needs. And so that's kind of why I left that in there.
So, I mean, what I was referring to is also the fact that there are like small dots in an area where everything else is classified differently. So can you do some filtering to see?
Yeah, I've actually done a lot of stuff, both spatial and spectral filtering. So I can, for example, instead of doing, maybe I can either spatially smooth or filter the image before I do the image processing. So then I'll take, let's say, a 3x3 grid of pixels, and I'll throw out the highs and the lows and just work with what's left. That will get rid of a lot of that. Or I can do and I can also do the same thing spectrally, or I can go ahead and process pixel by pixel, and then after the processing, do the, say, 3x3 filtering and throw out the highs and the lows. You get rid of a lot of that, and that I haven't showed you today because it was kind of secondary importance, and you know, it's going to go into some papers next year, but yeah, I've done a lot of that stuff. And of course, you know, if you do this was, you know, 1 meter, and if I do a 3x3 grid, well, now I'm down to 3 meter by 3 meter spatial resolution. So you lose something with that, and you gain something. And anyway, I've played around with a number of those things, and they work pretty well. Okay.
Yeah.
Now you guys can go back to doing something useful. So.
Well, this is great.
Yeah. Oh, and I gave Rob a directory that's got my presentation. It's got a bunch of papers if you're interested in, you know, this Hydrolite software or whatever that I'm using for the databases. You know, there's all info in there. So spread that around however you want.
Great.